In the last video, I left off on this theorem, and we are just about to prove it. So in this video, we'll prove theorem 4.1, which gives a sufficient condition for a graph to be k-connected. And that is, its degree has to be at least the ceiling of this number, n plus k minus 2 all over 2. As I mentioned in the last video, this is a nice proof to sort of see the general idea of a vertex cut. So we start with assuming that the theorem is false. We'll start by, assume, I'll type this. So assume to the contrary that there exists a graph that satisfies the hypothesis that is not k-connected. So being not k-connected, remember k-connected means that the removal of any fewer than k vertices leaves a connected graph and non-trivial graph. So if it's not k-connected, that means there's a cut set of size k minus 1, a cardinality k minus 1, that does leave a connected graph. So let U be a vertex cut with cardinality equal to L that's smaller than k minus 1. And so the claim, what I'm going to try and go for here, right, we're assuming to the contrary. The contradiction I'd like to get is that it doesn't actually satisfy the hypothesis. That is, I'll be able to find a vertex with degree less than this, the ceiling. So how does this work? Well, this is sort of a generalization of just there existing a cut vertex. So what the situation looks like is we have this set U with order of U less than or equal to k minus 1. And specifically, let's say it's L. Order of L is equal to, or order of U is equal to L. So we have these L vertices in here, and it's a vertex cut, and so it leaves a disconnected graph. So that means I have components. I have some number of components. I have at least 2 components. So I will pick a component of smallest order, because I'm trying to find a vertex with a really small degree in here. That is to go against the hypothesis. So let G1 be the smallest component of G minus S. Right? We know it's disconnected. I'll pick the smallest one. Let's say this is G1 here, this first guy. And I'm going to pick a vertex in there. And let's say let the order of G minus S, or of G1, order of this component be N1. And so what I can say is, since it's the smallest component, right, sort of worst case scenario is U only separates the graph into 2 components, but the smallest one will have at most the floor of half of the remaining vertices. So if I just focus in on my connected components here, there's N minus L vertices in just this graph in G minus U. And so I know that the smallest one will have at most half of them. Worst case scenario is we have half. And so that is less than or equal to N minus L all over 2. Let V be in the vertex set of G1. And let's think about what the highest possible degree it could have. So this will be my V in vertex set of G1. So degree of V, the most number of edges that could be coming off of V, well, I could have 1 to every other vertex in G1. And so that would be N1 minus 1 less than n1 minus 1. And then it might be connected to every other every vertex in the vertex cut. So the most the degree can be is n1 minus 1 plus L. It's possible it's adjacent to all of the vertices in U. Turns out this won't be enough. So let's see. N1 minus L, so this is, N1 is at most N minus L over 2, minus 1 plus L. Now L minus 1 here is an integer, and so I can bring this into the floor and find a common denominator here, so this will be equal to, this will be 2L over 2. I guess I could wrap this all together here. This would be 2L minus 2 all over 2. And so this would end up being N plus L minus 2 all over 2. Now L is, right, we know L is at most K minus 1. And so this is less than or equal to N plus K minus 1, N plus K minus 3 then, over 2. And, right, this is strictly less than the ceiling of N plus K minus 2 all over 2. Right, it's 1/2 less than this. And so if I switch the floor for ceiling, I'll have a strict inequality here. And then I have a vertex with strictly less than this, with degree strictly less than this quantity. So this is a contradiction. And so that finishes the proof. All right, so that's it for this one. It does give us a nice sort of quick check. If the degree of every vertex is high enough, then that'll guarantee that G is K connected.